Okay, so we are on to the last portion of our lesson, and we're talking about velocity time graphs. So velocity versus time graph displays velocity as a function of time. So at different times, points of time, whatever your velocity is, that's what this graph is displaying. So it's very different than displacement versus time, or position versus time, excuse me. It's showing you a different idea. So make sure you don't get these confused. There's a chart or graphic organizer that we're going to fill in at the end to hopefully help you with that. Again, this example problem is on D2L, so it's under velocity versus time graph example. So sometimes it's useful to display velocity versus time. So this thing is showing you the velocity of the object as time goes by. So taking a look at this graph, let's just kind of identify what's going on. And we're going to look at this graph and do some describing first. So if you take a look at the graph and it says describe the object's velocity for the following time period. So from 0 to 100 seconds, that's essentially like this portion of time. So 0 here to 100, that's what we're going to look at. So we're looking at what's happening to the velocity here to here. So I've already given that as an example to kind of give you some to kind of think about. So it says from 0 to 100 seconds, the object's velocity is decreasing from 20 meters per second to 0 meters per second. So the only thing I might add to this, I might put positive 20 meters per second because this is positive 20. Positive, again, since velocity is a vector, just means it's going to the right or up. This is going to represent something going to the right. And then if it was below this x-axis, so if I went down here somewhere, those would be negative velocities. So you might be like, well, I can't have a negative velocity. That's not true. Negative, again, it's just the direction, so it's moving left. So if we take a look at this, the object at the very beginning is going positive 20, so it's moving to the right, going at 20 meters per second. And then as time goes by, this velocity value is getting smaller and smaller. So it's getting decreasing, 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 all the way to 0. So at 0 meters per second, if you're going 0 meters per second, that means you have stopped. So this thing, in other words, you can kind of describe what's going on or what's happening to it, and we'll do that in the next part. So, so that's 0 to 100. Let's look at 100 to 200. So I've already started sort of the stem here with like starting the answer. So the object's velocity is, and we're just going to talk about what is happening to this line. So this line is remaining constant at 0 meters per second. So again, it's just staying, that line is staying. If you go over and read the velocity value, it's just staying at 0. Then for the next portion, the object's velocity is, if you take a look here, it starts at 0. It's increasing from 0 to 0 meters per second to, and I just need to look at the top, it reaches back to 20. So it gets back up to 20 meters per second up there at 400. So it goes to, and I'm going to say positive 20 just so there is no confusion as to which way it is moving. Okay, so that's that one. And then finally from 400 to 600, if you take a look at that one, it looks like, oh, okay, the object's velocity is remaining the same again, or remaining constant. And this time it's remaining constant at positive 20 meters per second. So we have, 4 sort of different types of motion going on in terms of like the velocity and how the velocity is changing. So there are some follow-up questions to this graph, and I should have, yep, I have the picture over here. So I've changed these to at what time interval is the object increasing velocity? So increasing velocity would be, if we look back at our graphs or our descriptions originally. So looking at these values, so it increases in the third section here from 200 to 400. So I can just write 200 to 400 seconds. If you're describing this line, the line moves away from 0 meters per second. So if you're going 0 meters per second, which means you're actually stopped, and you start moving in any direction, it doesn't matter if you're positive or negative, you're increasing your velocity. So this one, it happens from 200 to 400. Decreasing velocity is going to be the opposite of increasing velocity. So if we're talking about the idea, it's from 0 to 100 seconds. And in general, if you look at this line, the line moves toward 0 meters per second. So I have a decent way to help you guys sort of remember the two of those ideas. So if you imagine your speedometer, and I'll pull up or draw a picture of, an imaginary speedometer. Let's say 0 is over here, and somewhere in your car, depending on your car, you might have 100 or 120 miles per hour. And if you think about the speedometer, if you're increasing your velocity, that generally people think of that as increasing your speed or speeding up. So if you increase your velocity, and this is your speedometer gauge here, so this is the line. If you're stopped, you're at 0. As you increase, it goes away from 0. So when you step on the gas, this bar, it moves from 0 up to whatever you get your speed up to. So that makes sense. So that's increasing velocity, and that's moving away. So that works with this graph. Decreasing velocity would be the opposite. So you're already moving at something, and you're going to decrease velocity, which most people think of as slowing down. So if we did that, we'd be starting at kind of this value here, and we'd be going the other way. So the line would be going towards 0. So that matches up with your speedometer. So increasing, decreasing velocity, you can use your speedometer and think about how that behaves, and that matches up with the graphs on your paper. Moving at a constant velocity, that would be here. So moving with a constant velocity in our description was from 400 to 600. And if you look at that line, if it's constant, it's not moving towards, it's not moving away, it's just staying at the same level. So this is a constant velocity. And if you had a constant velocity on your speedometer, it would just stay still. So if you had a constant V, it's not changing. So it's not going up, it's not going away from 0, it's not going towards 0, it's just staying at whatever value it is. And then finally stopped, the stop time, that's from 100 to 200 seconds. And that has to be at 0 meters per second. So if you're stopped, your speedometer only reads that value. So it can only be at 0, that means stopped. So that is the only other thing. So some people might have answered, oh, why isn't 100 to 200 moving at a constant velocity? There is a constant velocity there, but the word moving is really the one that describes the difference. Okay, so that's just interpreting the graph. So looking at the graph, kind of understanding what's going on in terms of kind of the velocity, where it's at, how it's changing, describing that change. Last graph, we did position time, we looked at the slope, and we're going to look at the slope of the line on this graph again. So just to kind of fill in these blanks, it says, what does the slope of the line on a velocity versus time graph represent? So just like we had position versus time and the slope had a special meaning, the slope on a velocity time graph also has a special meaning. So again, slope, or M is the variable for slope from algebra class. It's just rise over run. So it's the change in, and the thing that's changing here is the velocity. So it's change in velocity divided by change in time. So this is delta V for triangle V over triangle T. And in physics, that has a very special meaning, and we're going to talk about that in a second. So this whole idea is on the next slide. It's known as the object's acceleration. So acceleration, you have probably heard of as well as a concept in your everyday life. So most times when people think things accelerate, they say that something is speeding up. So that is partially true, but it's not always have to be speeding up. So you could be increasing your velocity, You could be decreasing your velocity. You could also turn. So like all of those things change your velocity, and we'll talk about that. But the real proper definition of acceleration, and we'll go over this again next class, it's the rate of change of velocity. So it's what we just measured. It's how quickly an object's velocity changes. It's the rate of how much the velocity changes every second that goes by. That's essentially what we're talking about. Unit-wise, if we look back at this equation, I'll go back a slide and go back to our little derivation here. So, so A is for acceleration, and that's change in V over change in T. If you look at velocity units, the change in velocity would be a meters per second. And we're going to divide that by seconds. So it's meters per second, which is often written as meters per second squared. So this is a little bit confusing, but actually I think this setup with meters per second actually gives you better insight into what it actually means to have an acceleration and what's going on with that acceleration. So we're gonna get to the slope, and we'll come back to this idea of acceleration a little bit more next class. But just know that you take the slope of these lines and you find the acceleration. So one thing about slope, slopes can be positive, slopes can be negative. If you have a slope kind of going up and to the right, that's a positive slope. If you have a slope going down and to the right, that's a negative slope. If you have a flat line, that's zero slope. And if you have a vertical line, you have what's called an undefined slope. So in physics, we will never have this scenario. We will never have an undefined slope. In math class you do, but we will have positive, zero, and negative. So before we even kind of do the calculation to calculate the slope of each line, which is what it wants you to do here, and here's just the rest of those definitions that we were talking about. Oh, also accelerations can be positive or negative, just like the slope of these lines. So we're going to find those, but let's just kind of look at the line and decide whether it's positive or negative. So this one, it's going down, it's decreasing, or it's getting closer to zero in this frame. So that's a negative slope. This would be zero slope because it's horizontal. This is positive, and this one is also zero. So we're going to do the math. We should get those kind of values for those. So we're going to figure out from 0 to 100 seconds first. So again, we're doing the change in velocity over the change in time. And I'll start typing because obviously my handwriting is not the best, but I want to kind of have those triangles there because that's important. So for the first acceleration from 0 to 100 seconds, the change of velocity, if we look at this change of velocity, it starts up at 20 and it drops to 0. So change in is always final minus initial. So it's 0 minus 20 or negative 20. So I'll write out 0 minus 20 first. And then you're going to divide that by the time. So it's 100 minus 0. So that's just going to be 100. And you have similar problems on your web assignment like this. So I just want to make sure I should show it explicitly a couple of times. So this turns out to be negative 20 divided by 100, which is negative 0.2 meters per second per second. That's the right unit, or you could say meters per second squared. From 100 to 200 seconds, it's just 0 meters per second because it's not changing, like it's just a horizontal line. 200 to 400 is the next section that we are asked to find. So 200 to 400, it's going up 20, so it starts at 0 and it ends at 20, so it'd be 20 minus 0. And then you're going to divide that by the time, which would be the last time, which is 400 minus 200. So if I clean that up, it's positive 20 divided by 200, which is a positive 0.1 meters per second. Finally, the last one, again, is just a horizontal line. So from 400 to 600 seconds, that change in velocity over change in time, or the acceleration, is 0 meters per second. Because again, it's constant. And if you're constant, you don't have any acceleration. So those are the slopes of the line. So hopefully you can find slopes. It's not really that big a deal. You're just, doing the rise over the run calculation. You can look at it this way. So like I did it with the numbers there, but I could also have done it with something like just looking at the rise over the run. So this goes down 20, so that'd be negative 20. And then it goes over 100, so this would be 100. So it'd be negative 20 over 100, which is exactly what we got here as negative 0.2. If we do this section, it starts here and it goes up 20, and it takes 200 seconds going across. So this is plus 20 and over 200. So you rise first, then you run. So that it's the same numbers that we got here, and you get 0.1. So whatever way is easiest for you, whatever way makes sense. If you like the formula and you like the y2 minus y1 over x2 minus x1, do that. If you like just drawing on the picture and looking at how much it rises or falls divided by how much time it goes over, that's fine too. Okay, so that is the acceleration information. So the last part of velocity versus time graphs that we're going to discuss is the idea of displacement. So we've talked about displacement, or the change in position of an object, and we can figure that out from the velocity versus time graph. So how we can calculate that from here. So kind of looking at this, to determine the displacement of an object given a velocity versus time graph, you're going to calculate the area of the shape formed by the line and the x-axis. So it's a little strange wording, but it's an easier concept to kind of just show than to write out as an idea. So I'm going to do a little bit of coloring with different type ideas. So I'm going to highlight kind of this idea of the area of the shape formed by the line and the x-axis. So this is our line that represents the velocity, and the shape that it forms with the x-axis would be this that I'm drawing in here, and this is kind of a yellow triangle that I'm highlighting in here. So this yellow triangle, the space between that line and the x-axis. So the x-axis, just to establish where the x-axis is, just in case anybody's confused, is this horizontal line going across at velocity equals 0. So we are looking at this area, or this boundary between, or the area bound in by this red line, and then the y-axis and the x-axis here. So that's our first area. And I've already worked this one out as an example, because I feel like that's helpful to kind of see it and figure it out. So we're going to look from 0 to 100. So again, just kind of writing in these numbers. This is 100 seconds. And we said that this was at 0, and this was all the way up at 20, and it's a positive 20 meters per second. So hopefully you remember the area of a triangle, because that's the shape. So you just have to decide what shape it is and then find the area of that shape. So a triangle is 1/2 base times height, or 1/2 length times width, depending on how you were taught it. But if we plug in these numbers for here, it'd be 1/2. The base is 100 seconds, and the height is positive 20 meters per second. And if you just multiply those out, so half of 20 is 10. 10 times 100 is 1,000 meters, and it's a positive 1,000 meters. So that means that this object in the first 100 seconds of motion moved 1,000 meters in the positive direction. That's all it is. So you're just going to look at the kind of areas and try to find the areas of the shapes that are bound. So we just did this one, which I'll maybe call part 1. Okay, so question 1. Question 2 on the next slide. We're trying to find 400 to 600 seconds and the displacement there. So again, the first thing you need to do is kind of maybe highlight where those different areas are. So I'm just going to do the x-axis again, just so we know where to stop our line, because you always stop on the x-axis. And we're going to make a section for 400, which is that time, to 600, which is that time. So that is that area that I'm just kind of putting those lines in. That is the area that we're trying to figure out for this time period. We're trying to figure out the displacement for it. So again, you just got to figure out the shape. So this hopefully you recognize as a rectangle, which is just length times width. So the area equals the length times the width. And if we look at the length, and it doesn't matter which way you call the length and which way you call the width, I'll say the length is sort of the height, and then the base is the width. So it looks like it's going positive 20, because that is how tall this triangle is. So if you look, you go from 0 up to positive 20 for that, and here to here. So that's positive 20. And from 400 to 600, that's 200 seconds. So going across, that's 200 in that direction. So kind of finishing this up here. So it'd be 200, or I'm sorry, positive 20 meters per second, because that's the velocity. And we're going to multiply that by 200 seconds, which is the time. And if you multiply those together, you get a positive 4,000 meters per second. So, so that is how far it traveled. It traveled, 4,000, or it was displaced, meters per second, sorry, it's just meters. It's displaced 4,000 meters in that time period, and that's what you would do. From 100 to 200 is the next section. So in the next section here, so it's 100 to 200. If you look at this here, 100 to 200 is it is not an area. There's no space because it's a line on top of a line. So so that answer is very simple. It's just 0. So it doesn't travel any meters. And that makes sense, right? Because you're going 0 meters per second for 100 seconds. So if you're going 0 meters per second, that means you're stopped. And if you're stopped, you're not moving anywhere. So there's no displacement. So there's no change in position. So the last one here is just this section of this triangle. We're gonna try to figure out that area. And we did a triangle before, so this should be fairly straightforward. So again, you got to figure out how far it goes across, which is 200 seconds. And it goes up 20 meters per second. Positive 20 up here at the very top. And it's a triangle, so kind of filling out the triangle information. It'd be the area of a triangle is equal to 1/2 the base times the height. So it's 1/2 times the base is 200, and that's seconds, and then you multiply that by positive 20 meters per second. So this one turns out to be 2,000 meters, and it's positive. Later on, when we get into another type of, another example of this, you'll see that I'm not just being extra when I do these positives and negatives for these values. So it's going to make a difference later on. And it makes sense that it's got a positive displacement because it has a positive velocity. So if you have a positive velocity, it means you're moving in the positive direction. So if I have a positive velocity, say I'm going to the right, there's no way that I end up with a displacement. So I started here at this asterisk. There's no way I can move to the right and end up with a negative displacement. It doesn't make any sense. So the velocity vector direction and the displacement direction always have to agree. So even though in the first part we talked about, and just to kind of reiterate this, we talked about this part here, this first 100 seconds, the object was decreasing its velocity. So if you imagine the car is braking, but it's braking as it moves forward. So it's still got a positive velocity. That velocity is just getting closer and closer to 0. So just like in your car, you're driving down the highway and you see the traffic light turn from green to red, you hit your brakes and you are still moving forward towards the light. You're just slowing down as you do that, or decreasing your velocity. Slowing down and speeding up are sort of bad terms because, again, then you think about speed instead of velocity, and these graphs show velocity. Okay, so I'm going to stop there because we've covered, I think, everything that I wanted to in this lesson. Next time, we are going to start off with this summary graphic organizer. So if you want to take a look at that and think about what those things are, I would say to do that. Also, I will also kind of go over some answers, and we'll practice another velocity time graph, which is also in the week 1 or unit 1 kind of week 1 folder on D2L. And we will also kind of be working on some lab simulations. So I'll probably make a video or two to help you get to the different lab simulations and make sure that you're on track to answer those correctly. So I'm going to sign off and wish you guys well, and I'll talk to you later.